In earlier videos, we've already stated that to ensure good combustion and therefore good energy transfer from the chemical energy of the fuel into the airstream, it's necessary for the air and fuel to mix at the molecular level. The unforced diffusion of fuel into air, and vice versa, is controlled by Fick's law. Here, C is the concentration of a substance diffusing, either air or fuel, and is typically measured in moles per cubic meter. Y is the distance into the fluid, and D subscript Fa is the diffusion coefficient or diffusivity of the fuel into the air, or the air into the fuel. They both have the same value. The flow flux resulting from this is J, which is measured in moles per square meter per second. So dC by dy is a concentration gradient in the y direction. Note, however, that it's also possible to have forced diffusion, for example by an electrostatic force acting on ionized components. And also note that d changes with fluid parameters, for example the temperature. Now, to aid these calculations, several authors have introduced a variable which is known as the mixing layer thickness and given a symbol delta. This is defined as a region where the mixing has been successful enough so that the molar fractions of air and fuel differ by only 1% from their required values. It can be shown to be given by the formula delta is equal to the square root of dFA times x over uc, where uc is the speed of travel of the flow in the x direction. So given this, the only tricky thing to find is the diffusion coefficient dAf. There are a few approaches which can be used for this. Firstly, as discussed in Hypersonic Airbreathing Propulsion, the book which I mentioned in earlier videos, a formula for it can be derived from basic fluid mechanics. This uses the dynamic viscosity and the Schmidt number, which is approximately 1 for most fuels and about 0.2 for hydrogen and air. The dynamic viscosity for air is given approximately by the equation shown below. An alternative approach is to derive a value from kinetic theory. For example, in SI units we could use this one. Here n is the number density of molecules, which we can also get from kinetic theory. It's equal to the pressure divided by kT. D is the average molecular diameter of the mixture, and mF and ma are the masses of the air and fuel molecules. The final approach to getting a value for the diffusion coefficient is to use one of the few measured values, for example in the book by Mills for this parameter. The theoretical values calculated with kinetic theory seem to be closer at high Mach numbers to these experimental values. The approach outlined above assumes that the air and fuel are moving along at exactly the same speed. In the analysis presented in the book Hypersonic Airbreathing Propulsion, it's shown that the result when they're moving at slightly different speeds, not fast enough to cause turbulence, is very similar. When the difference between the flow velocities of the air and the fuel becomes large enough, the flow becomes turbulent. This is indicated in the classical way by the Reynolds number. Swirls appear in the flow which entrain and enfold the fuel and air together. These rolls, as they initially appear, are called Kelvin-Helmholtz instability, and they degenerate into chaotic turbulent flow further down the duct. This dramatically increases the area of contact between the air and the fuel, and also the concentration gradients, which speeds up diffusion and helps mixing. On the downside, however, if the turbulence reaches the duct walls, it causes an increase in drag. And secondly, remember that the thrust is equal to m dot v. And if VE is lessened by the appearance of turbulence, the thrust will correspondingly decrease. You can possibly see intuitively that this is likely to be the case. This is roughly equivalent to saying that the turbulence causes an increase in entropy of the flow. And as you might remember, we'd like our processes to be isentropic if possible, so that all the energy is contained within the flow and available for thrust.